Okay. Hi, everybody. Thanks for coming to the seminar of the International Institute of Physics. And today our speaker is Emanuele Orazi from the School of Science and Technology here at UFRN. And Emanuele received his PhD from the University of Rome, Tor Vergata. And he did a couple of postdocs, one in Polytechnic University of Turin, and in 2011, he came to Natal first as a postdoc of the institute. And since 2015, I think he's a professor at UFRN at School of Science and Technology. So Emanuele works with gravity, supersymmetry, and general aspects of quantum field theories and gravity. And today recently he got interested in modified gravity. And today he will talk about, his approach to modified gravity. Well, thank you, Emanuele. So the word is yours.
Thank you for the invitation and giving me the chance to present my research. Okay, so let's start. I must apologize because it's introductory at the beginning, but later will be a little bit technical. Okay. So as far as I know, the level here, we're trying to introduce the argument to new students. There are a lot of students here. So the first part is dedicated to you, okay? Mostly. Okay, this is the plan of the talk. Not that brief introduction. Then we will talk about parallel transport and the link with conformal invariance. And after I will introduce you to how to gauge a conformal symmetry in a gravity theory and how to build any modified gravity that is conformal invariant. And then I will show you how to solve, how to solve the field equations, part of the field equations. And finally, we will talk about not a modified gravity, still a modified gravity, but basically it's general relativity with conformal symmetry. That is the simplest example you could imagine. And finally, I will give a sketch on how to generalize more cumbersome theories like Eddington-Sparrow-Born infinite gravity. Okay, so the main objective of the talk are the following. I want to explain why I want to give you a justification, very strong justification to say that any gravity theory that is studied using the approach of metric-affine, in the metric-affine framework, it's mandatory to introduce this conformal symmetry. You don't have any choice, otherwise it's not consistent. Okay. And I will show you how to build and solve the field equation associated with the connection. Okay, we are talking about metric-affine approach. Soon I will explain what does it mean, but basically you have a field equation that is only for the connection, and I will show you how to solve it in general. And finally, we will talk about generalization of general relativity and consequences. Okay. So the starting point, anyone that attended a course on general relativity knows that the main breakthrough of Albert Einstein was the geometrization of gravity theories. And this implies that the space-time curvature is responsible for the gravitational interaction. So when we deal with if we want to model gravity, you need to model the space-time using a differentiable manifold. And in a manifold, there are two concepts that are separated in some way, at least mathematically. One concept is the metric, okay, that is related to distances, angles between vectors. And the other concept is related to the parallel transport, how you transport consistently a vector through the manifold. So basically, the variation of the vector should be proportional to what is called a phi connection. And this is the basis to define a consistent concept of derivation, that is the covariant derivative. Okay, these are very basic stuff. Just to remind you that there is this possibility to separate these two concepts. They usually are related in a general relativity, since a priori you assume that the connection is related to the metric, but this is not so mathematically. Okay, so if you assume that the metric connection are separated, then we have to distinguish the very well known metric compatible approach to gravity, where you assume that it holds this condition that can be, that we refer to this condition like as metricity condition, and this automatically imply that the Christoffel symbol of the metric is the connection. I add this circle, math circle, above the connection to say that this is the what is called the Levi-Civita connection. Okay, so it's related to the metric in this way. So this is the common approach, the standard approach to gravity. But soon was discovered that it's possible to disentangle these two concepts, and it was Palatini the first to propose this. And we have this metric-affine approach to gravity, where actually the metricity condition is not necessarily zero. It's important to notice that the connection, the symmetric part of the lower indices of the connection is the only one that appear here. The antisymmetric part is zero due to this functional dependence. So we can assume in the metric-affine approach that the antisymmetric part of the torsion is not zero. And even the Ricci tensor, the antisymmetric part of the Ricci tensor is not zero, that usually is zero. At the moment, no. But so metric-affine gravities allow the introduction of new geometric structure. The non-metricity tensor that recently became very famous, there are a lot of papers on this, that basically measure which is the deviation between the metricity condition and in the new theory, and torsion. Torsion is well known as this antisymmetric part of the Levi-Civita, of the connection. And other quantities, these are very fundamental. There are other quantities that are less explored, like the motetic tensor, that it doesn't need the introduction of the metric. It's another saturation of the indices. When you are introduced to the definition of the Ricci, you know that there is a specific order of contraction of the indices. Here is different, is the first and second of the Riemann tensor. Yeah. Yeah, it's because of the antisymmetry. The first two indices are antisymmetric, so it goes zero. I don't give all the properties of the metric-affine gravities, but just to mention that the only symmetry that you retain for the Riemann tensor is the antisymmetry in the last two indices. The other one you lose completely in a general theory. Okay, so what's the deal today? Basically, the main question is, you can use these quantities to formulate new gravity theories. Which are the relations between these theories? Maybe they are related in some way, so the physics beyond that is the same. Okay, and to explain how many the big plethora of theories that you have, consider that in general you can write can be proved that in general you can write an affine connection as a sum of three quantities. The first quantity is the well-known Levi-Civita connection, that is the Christoffel symbol of the metric. The second one is called contortion tensor. It's related to S, that is the torsion. And the third one is called this formation, that is related to no metricity. No metricity is basically this tensor that we introduced before. Okay. So which is the meaning of these quantities? Okay, the meaning of the Riemann curvature is well known. It measures the deviation, the vector, when it's transported along a closed path. The torsion measure the deviation of vector where they are, when you use the usual sum rule, when you commute the sum rule between vectors. And no metricity measure the basically it affects the length of the vectors along a path. So if you introduce no metricity, you are allowed to modify. It's a function, the length of the vector along a path. It's not constant. So this is a sketch of how many gravity theories you can find. So depending on what you put to zero, you have a different gravity theory. But the mother of all is the metric-affine gravity. So metric-affine gravity doesn't assume anything. So you have all the quantities, everything you can imagine. But from this gravity, you can put some constraints, like say the no metricity is zero, you have the Einstein-Cartan gravity, you still have torsion. You can put the torsion to zero and you have no metricity, so you have the torsion-free gravity. This is becoming quite famous. That is the teleparallel gravity when you put the Riemann to zero. Notice that the Riemann to zero doesn't mean it's the Riemann before going on shell for the connection. So maybe after going on shell, it's not zero anymore. This teleparallel gravity, it's interesting because it's quite natural to describe gravity using torsion as the gauge field that describe gravity. So it's quite natural. So another one is Riemann gravity. That's well known. It's not worth to present it. Weissenbach gravity. You put the no metricity to zero and the Riemann tensor to zero. Symmetric teleparallel is a variation of the teleparallel where torsion as well is put to zero. And finally, Minkowski gravity. You put everything to zero. Well, if the curvature is zero, basically all the paths are parallel. This is the tele. I don't know, but parallel, it's justified. Okay. So before, I want to focus your attention on the first one, this Einstein-Cartan gravity, because we have to deal with that. Basically here, you still have torsion. So the metricity condition here still holds, but inside the connection you have torsion. So this is not the Levi-Civita connection. In fact, if you solve this equation in general, you don't need to have zero torsion. You could have a contribution. So this metricity condition still holds in this Einstein-Cartan gravity. Okay, another important concept that is needed to understand what is coming is the conformal symmetry. So there is some misunderstanding when you talk about conformal symmetry in a gravity context. And the misunderstanding is the following. In general, a conformal transformation is assumed to preserve angles. This is the common law. the common definition. So in general, you can have a relation that basically the metric that describe, that basically encode the method to measure the angles uh, could change for a change of variables up to a factor. Okay, so in general, you can make the transformation without changing the space-time and changing the functional form of the metric. However, we need to distinguish between a conformal isometry that basically say that the metric remain the same. So you have this. Basically, it's immediate if you assume that h is equal to g, or local conformal, even called the Weyl transformation, where basically you don't change coordinates. So here you have a diffeomorphism, here not. The coordinates are the same. In some way, this is much simpler than the previous one. So this creates a misunderstanding, because you can think, okay, but can I say that if we have this symmetry, then the space-time conformal transformation are implied in some way? The answer is no, at least not all them. Okay, so there are different concepts. So we will refer to conformal symmetry when we are talking about this Weyl symmetry. Okay, this Weyl transformation. This is important. Okay, after that, we can introduce what was known before. Okay, so in 1918, Weyl proposed this theory that is basically is known to anyone, I guess, trying to unify gravity with electromagnetism. He proposed another symmetry. So he said, okay, if we perform a Weyl transformation and we add a gauge transformation, at the time was not the name, actually was not this, they didn't know what a gauge transformation was. In the modern language, basically introduced a gauge transformation. So if we introduce these gauge fields W mu, that gauge transform is in this way, then we can replace the metricity condition with this new condition. So you see that it appears a no metricity here that is proportional to the Weyl tensor, this gauge field that is called Weyl vector. What is the key property of this proposal? So here you still have the Levi-Civita connection, okay? But basically, to have consistency, to be symmetric under a gauge transformation, you have to assume that the connection is no more the Levi-Civita, but you have to add three pieces that include this Weyl vector. So this was his proposal. It didn't work well. Okay, it worked because the claim was that this transformation was able to introduce this gauge field that could describe electromagnetism, but it didn't work for a simple reason. When you introduce no metricity, like it did here, then it's not consistent, since the dependence on measured length on space-time paths crash with the concept of one absolute measure in quantum mechanics. So it didn't work. Was refused and abandoned for a long time. But in 1982, there was another proposal. Okay, the Weyl symmetry was not completely abandoned, because it was used in other contexts. It was generalized gravity in such a way to accommodate these problems. But the real breakthrough for us was the proposal of Obukov on 1982. He said, okay, let's assume they still work the metricity condition. If it happens, what we can redefine, instead of adding a no metricity here, we can redefine the connection in this way. And then if we identify the gauge field with the torsion trace, then everything becomes consistent, that the gauge transformation act on the torsion trace. But to do that, you need another ingredient. First, you have to formulate everything in the metric-affine approach. In the metric-affine approach, you gain a new symmetry, that is this one, the projective transformation symmetry, that basically leaves invariant the Riemann curvature. And so you can transform the connection in this way in order to define a consistent theory. Okay, this is the main point of this paper. What is the advantage of first, I forgot to mention that everything here is described in Einstein-Cartan geometry. That's the reason why I said that it's important for us, this geometry. So the advantages of Einstein-Cartan formulation of conformal gravity are the following. First, the Riemann tensor is not to be EPT invariant. Second, so you can formulate any gravity theory that is invariant for this symmetry. Second, the Stuckelberg terms are introduced in a very natural way. This allows to say if you can build a conformal invariant gravity theory, then you don't need to set a scale. Basically, we can justify the existence of the Planck scale that is given by the breaking of the symmetry. After all, another point is that you can model cosmological scenario in this way. However, a couple of questions remain unanswered. That are the following. Is there a fundamental reasoning to introduce this symmetry? And the second question is, can you formulate all this in a metric-affine formalism? Because he formulated in a Einstein-Cartan formalism that is a lower level. Can this be made more general than that? So the idea is the following. And basically now we skip to the part that is kind of new. And this proposal has been given in a paper that I will mention at the end in the references by me and some of my collaborators. And the main point is that in a metric-affine theory, the parallel transport is not consistent. And I explain you what does it mean. And to make it consistent, you need to introduce this symmetry. This is the main message of this talk, basically. Okay, so this is the concept. What happens? You know what is parallel transport. Basically, you put the directional derivative along a path to zero. Okay, this is the common law. However, if you assume that you are in a metric-affine theory, as I mentioned before, a priori you have a no-metricity. And no-metricity said that basically along the path is not established, which is the measure, the length of the vector. So this means that you have to add another term here. So if you want that the vector multiplied by a function still is parallel transported, because actually if you take a vector and you take another vector, you just need them to be parallel, but you don't have to say anything about the length. So the way to accommodate this is to add a new term here. Well, you can find this equation in textbooks, in academic textbooks. So this is more or less known. And the same happens for the geodesic equation. The geodesic equation, you should put this left-hand side to zero, but now you have to add another term. And but the problem is you cannot have an equation that depends on this lambda. that is a function of space-time. So in some way, you have to remove them. So there is a recipe to, not a recipe, let's say the main question is how I can preserve the notion of parallelism when I have this lambda here that is arbitrary. Well, the idea has been, the idea, you can find this idea in a very old book by Eisenhardt, 1927, that basically you anti-symmetrize the previous equation. You say, okay, let's say, can I do a transformation of this connection that preserve the notion of parallelism? And the answer is that you can, and you get this transformation that is called projective transformation. So basically, this transformation preserves the notion of parallelism. But the problem persists, because even if you now know that you can still define an invariance of parallelism when you add this term that is arbitrary, but when you want to solve these equations, you cannot, because you still have this arbitrarity. The problem is here more, okay, how we solve the problem at the level of the geodesic equation? Basically, geodesic equation is not a reparametrization invariant. So a reparametrization could cancel this term. But this doesn't work. This is what you find in common textbook. But this doesn't work for the parallel transport, because this is a reparametrization invariant. So if you do a reparametrization, the problem persists. So how you can solve that? Well, now that you know that the parallel transport is the same along the manifold, if you redefine the connection through a projective transformation, you can use that to remove this term. Actually, if you do that, you find that the only thing that you have to do is to identify this a mu with the derivative of log lambda along the path. If you do that, then you can remove this term without affecting the properties of parallelism in the manifold. And you can say something more than that. Actually, another thing that is quite annoying is that when you use the common approach of textbook to remove the additional term choosing a specific parameterization, this tau, then you get an equation that is not reparametrization invariant. If you add this symmetry, then you can still maintain this form of the geodesic equation, reparameterize, and reabsorb the reparameterization term into a projective transformation. So you get invariance of this of the geodesic equation in the simplest form. So this is to explain you that actually to have a consistent concept of parallelism in a theory that doesn't preserve in general the length of the vector along a path, you need to introduce this specific symmetry, okay, where a mu is actually a derivative of something. And this reminds you some kind of gauge transformation, but a gauge transformation that is already embedded into the connection. And this is basically the new ingredient that you add. So the next step is how to include conformal symmetry in a metric-affine gravity theory. That means how to include this symmetry in a metric-affine gravity theory, and how to build a consistent action for these theories. Well, the idea, the new approach is this: we identified where is this symmetry that actually was hidden in some way. So the idea is the following. Okay, this is the gauge transformation that we want to include into the gravity that we are dealing with. So if we want to define a covariant derivative that is consistent, that means when you transform it, the connection transform in this way, it means that the tensor that you are considering should transform in a way that has a conformal weight that is related to the uh, to the properties under diffeomorphism. As you can see, depending on the covariant and contravariant indices that you have to add this conformal weight n minus m. In this way, everything is compensated and it cancels in a proper way, and you can define a proper covariant derivative for this symmetry. So this was not known before. And what is really interesting is that what is the difference between the Weil approach? The difference is that here you don't have to add a new gauge field. The gauge field is already embedded into the connection. So it was hidden inside there. Actually, there was some hints pointing in this direction. I will explain you which hints later. In particular, this kind of transformation applied to the metric, gives you exactly a conformal transformation. So this is why the name of conformal transformation, because actually so far here is a dilatation symmetry, but now it becomes a conformal transformation or Weil transformation. So we still have to identify where is this gauge field. So if we take the trace of this, we get this equation. Okay, we take the trace of the connection. So you are tempted to say, okay, the gauge field could be that is the trace of the connection, since it transforms exactly how it should be. But actually, you cannot assume that the trace of the connection is a gauge field, because it's not a vector, because the connection doesn't transform properly, doesn't transform as a tensor. So the trace as well does not transform as a vector. The right way to identify is to decompose the torsion. If you decompose the torsion in its irreducible reducible parts, you discover that there is one component that is exactly a vector. This is a pseudo vector, and this is the complete antisymmetric part. So if you basically this transforms as a vector, and if you take the trace, you realize that actually this S mu, that is called the torsion trace, is exactly the gauge field that you are searching for. So why there was a hint pointing in this direction? Because if you take a metric-affine theory, if you check in this paper that I co-authored, if you take any metric-affine gravity and you solve the connection field equation, you will find that 4 degrees of freedom are left free. You cannot fix 4 degrees of freedom. There were papers in the past saying maybe this is a problem, so we have to add some term to break this symmetry, to fix this 4 degrees of freedom, because the theory has some problem with this. It's not possible that 4 degrees of freedom are left free. Basically, these 4 degrees of freedom are exactly these degrees that are included in this gauge field. So basically, it was already there, but nobody understood that this is part of a hidden symmetry. So resuming, these are the gauge transformation of the theory, the conformal gauge transformation. And so we identify this B mu is proportional to the torsion trace, and then it transforms exactly with this d mu alpha. And the next step is how to build a conformal modified gravity. Well, this is quite simple, because you just have to construct terms that are invariant under this transformation. But to do so, you are forced to introduce a compensator. That is you can call it, it's a scalar field, you can call it dilaton. And under gauge transformation, it has to transform in this way. And obviously, covariant derivative, as you can see, this scalar field, contrary to what happens with asymmetry, is charged under this symmetry. So you have a connection B mu for this conformal symmetry. Okay, after introducing this dilaton that is necessary to compensate the transformation to construct invariant terms, then the game is easy. Okay, you can do that. And in particular, nothing forbid you from introducing a kinetic term for the new gauge field and a kinetic term for the scalar field. And so we add these two terms that are the standard terms. Here you have these covariant derivatives, as I mentioned before, and here you have the field strength associated to B mu. Just a remark that I am not mentioning here. If you are tempted to follow the idea of Weil and say, could it be electromagnetism? There is something that forbids to describe electromagnetism in this way. And the reason is that this gauge symmetry that you are dealing with has a parameter that is not compact. So electromagnetism is the gauge theory of U1 that basically has a parameter that run on a circle. Okay, but here you cannot do that. So this is usually called the R plus symmetry. So basically, it runs all the reals, positive reals. So this is not electromagnetism. It cannot be electromagnetism in any way, unless you assume that the parameter is imaginary. And so as you can see, I introduced these two parameters, psi1, xi2, that can be put to 0 without affecting the symmetry, because these terms are individually conformal symmetric. So if you open up this covariant derivative, you realize that actually introducing these two terms is equivalent to introducing a Zuckerberg field. So basically, you understand which is the rule of phi. Phi is the Zuckerberg field of the gauge field B mu. So B mu is basically massive. For the people that do not know what is a Zuckerberg formalism, basically is a way to introduce in a gauge invariant way a mass for a gauge field. So you need a compensator to do that, because actually the mass breaks gauge symmetry. In this way, it's not broken. So it comes quite natural. And this introduces the simplest symmetry breaking mechanism that you can imagine. So summing up, adding the kinetic terms is equivalent to introduce a symmetry breaking. Okay, so in the last part of the action that could describe a gravity theory is the matter sector. The only remark about this matter sector is that you just can introduce these psi are not fermions. Fermions actually are not treated in this theory so far, but it's just a collective way to say that you could have other fields. And basically, what is important is that the compensator appears only through its derivative or bare, but cannot have a flat derivative. So it's basically minimally coupled. Okay. Another remark that is worth mentioning here is that we are generalizing previous approaches where basically, usually in modified gravity, you tend to introduce just a minimal coupling. Here, you break the minimal coupling rule because actually now the matter sector depends on B mu here. So B mu is part of the connection. Being part of the connection, this derivative is not 0, and what is called the hypermomentum is not zero, and this means that it's not minimally coupled. So this interaction now is allowed. It's minimal in the sense of the new gauge symmetry, but it's not minimal in the sense that it's coupled to the connection. Okay. And another non-minimal coupling is the coupling between the compensator and the Riemann that is in the gravity sector. So the answer is, can we solve for these theories in general the field equations? And the answer is yes. So I skip the technical part. Basically, you can check on the papers how to do that. But basically, this is the field equation for the connection, and the connection it does not appear explicitly. You have to define this tensor U through the derivatives of the gravity sector with respect to the Riemann. And what you find is that what is important here is that actually you cannot solve for any theory, but you can solve for theories that depends only on the symmetric Ricci. Okay. So for the symmetric Ricci, you define when you derive the gravity Lagrangian with respect to the Ricci, you define this Z tensor. And this Z tensor basically is the main ingredient to solve the equation. And the solution is the following. You find that the connection is related to the metric through this equation. You recover some part that remind you the Christoffel symbol, but in terms of another metric that is a function of this Z tensor that I introduced before. Okay, and you have another term that is basically the torsion trace. And you can see 2/3 of S nu is exactly the field B nu that we introduced before. So this is the general solution, the connection field equation. But the main point here is that, okay, you find which is the relation between the connection and the metric and the new gauge field, but you have an additional field equation. So the field equation associated to B mu and the field equation associated to the new compensator. And this is where the new physics lies. So in particular, you can see that you can use the symmetry, gauge symmetry, to fix a gauge that is called a unitary gauge when phi is equal to 1, and say, okay, do we recover the common result, the usual result? And the answer is no, there is something more. To make you understand better what's going on, let's consider the conformal GR. So this is the simplest example. You just couple phi squared to the Ricci scalar, to the curvature scalar, and what you get is basically something that reminds you Brent-Dicke theories. If you solve the field equation of this theory, then you get this solution. Basically, the so-called auxiliary metric is related to the physical metric through a conformal transformation that includes this phi squared. So even if this result is quite easy to obtain, it's still enough to understand where the new physics is coming. Okay, to make it explicit, this is the expression, the connection for this conformal general relativity. And you see that no metricity appears here. And then you can say, okay, let's discuss the theory in the simplest frames possible. Let's assume that phi is equal to 1. Or better, even better, we can do, since this is basically a conformal transformation, we can we can say if we perform a gauge transformation, a conformal gauge transformation of this type, which is the theory we obtain. And basically, you still have no metricity after this transformation, and you reduce the connection to this simpler one. So basically, if you generalize general relativity adding this conformal symmetry, you have a solution for the connection that is basically the same that you expect plus this part that is, is taking into account the new gauge symmetry. In particular, how you recover general relativity? If you set xi1, xi2 to 0, that means you put the kinetic terms to 0, then you discover that this B mu is not constrained by the field equation. So you recover this freedom to introduce this gauge, this torsion trace. So you can set to 0 and you recover general relativity. But if you have a kinetic term, so you assume that this new field associated to this hidden symmetry are physical, dynamical, then you cannot do that. So you don't recover in any way general relativity. In particular, what is interesting is that if you start analyzing the field equation associated to B mu and phi, then you realize that these two field equations are the equations that are basically encoding the new physics. And in particular, you can say, okay, let's fix phi to 1 to see if we have some simplification choosing a gauge fixing for this theory. And then what you get is that you still have a curvature. Actually, the scalar curvature is determined by the gauge field associated to the hidden symmetry. What is this telling us? Which is the message of this? Basically, if you choose to study a gravity theory, any gravity theory, with the metric-affine approach that is quite natural, it's well used. For instance, in supergravity string theory, usually they use the metric-affine. They don't even think about the metric formalism. They don't assume a priori the metricity condition. So if you assume that the right framework is the metric-affine, you have to modify your notion of parallelism in a consistent way. If you do that, it means that the theory should be conformally invariant. If it is conformally invariant, it means that it's quite natural to add kinetic terms for this new symmetry, for these new fields. If you add these new fields, then the space-time curvature is determined by these new fields of this hidden symmetry. And it's interesting because this B mu is massive, so the interaction of this field is short range, okay? It's mediated by this mass. And so this reminds you a possible solution for gravity problems that affect the theories of gravities nowadays. So basically, we are searching for some kind of interaction, of long-range interaction to describe that resemble gravity, to model in some way dark matter, dark energy. This is even this problem with lambda CDM that you have these divergences for the vacuum energy, all these can be related. I don't know how, I don't know if it's possible, but could be related to this new interaction, to these new fields that determine the curvature, to a contribution of this new field that determine the curvature of space-time. Okay, and this is a very strong justification for this. And even cosmology could be affected, and stellar dynamics could be affected by this kind of equation. And as I showed you, there's no way to remove this dependence of space-time curvature from this hidden symmetry. So it's not that you find a gauge fixing or a particular frame where you remove. It's there and you cannot get rid of that. Just to give a sketch of the power of this method, you can apply all this not only to general relativity, but to any gravity theory. One very cumbersome gravity theory is the heading to inspired Born-Infeld gravity, that basically is a gravity that reminds you the Born-Infeld electromagnetism. The difference is that you have, instead of the electromagnetic field, you have the Ricci. So you can see that the action is described by a square root of the determinant of the metric plus a parameter multiplied by the Ricci. If you simply add a phi squared here and here, then you get automatically a theory that is conformal invariant. So even in this case, obviously this wasn't studied, and I didn't check what happens with the field equation, but this is just to tell you that this symmetry is not can be applied to any gravity theory. Okay, so concluding remarks. As I said you before, any metric formulation of gravity should encompass this conformal symmetry, and you have at the end of that time to talk about this Stucker-Bell mechanism that is at work here, but it's quite simple to imagine how it works. You basically fix the gauge, then you get a mass, a scale. You get a scale through this gauge field B mu. And as I showed you, even the simplest case of conformal GR, the geometry of any solution is affected by the dynamics of the new gauge field included in the theory. Is affected by a modification, the modification of the space-time curvature. Obviously, this new framework demands further study to understand observational effects. So basically, this is a possible line of research for the future. It's not just a result. There's a lot of things to do here, and I don't have much time to do that. So any help is welcome. Okay, so future developments. There is a problem here that is how to include fermions in the treatment. And this is a very old problem that is a problem not of these theories, but of metric-affine theories. I'm actively working on this problem that actually is standing there. There is a way that was being proposed long ago that is through infinite representation for the fermions. So it works, but it's very cumbersome. So I'm searching for a way to include fermions in a metric-affine theory in a more efficient way. Then exact solution of this conformal gravity. Well, this is an important point because as you can, since it reminds at the level of field equation, this B mu field is like very similar to electromagnetic field. So you can say we can propose solutions like Rystrom black hole to describe all this. But the problem is that this field is massive, and there are not known solutions for a gravity theory coupled to a massive gauge field. Actually, there are solutions at infinity. And this brings you to the third point, that is application in holography. So you can find a solution to these theories, but just at the boundary. And so application in holography means if the symmetry exists in the bulk, what is the meaning in the boundary? Since you have solution, you can check which is the meaning of this symmetry in the boundary. And this is maybe work in progress, not sure. And obviously implication for cosmological models. And these are working on this with some of my students. And the idea is that since you have a new scalar field, instead of approaching gravity theories using the scalar tensor mapping, you can directly approach using this phi, this new scalar field, to model inflationary scenario. And this is a work in progress as well. And then another interesting point is that, as you saw, the torsion has other irreducible components. Could then be related to other hidden gauge symmetry. Well, this is very interesting because maybe that there is another component that is related to another hidden symmetry, but I'm not sure. I still have to fix this point. And these are the main references. Okay, all this is in a JCAP paper by me and collaborators, consistent metric-affine formulation of modified gravities. And to understand what's going on here, you need this other paper, Generalized Solution of Ricci-Based Gravity Theories in General Relativity. This is the paper that I mentioned at the Obukov, Conformal Invariance and Space-Time Torsion. Basically, what is surprising, I want to, and there is this other that is interesting on the equivalence of the Einstein-Hilbert and Einstein-Palatini formulation of general relativity for arbitrary connection, but that is a pause. What is interesting is that the community didn't notice this symmetry, even if there are these papers that are quite old. This is quite old, this is more recent. But what took me almost 3 years to publish the paper related to this symmetry is the fact that is so simple in some way, and so amazing that it exists, a hidden symmetry that was quite strange that nobody noticed before. So I have to check for years for looking for references of someone that did this before. I actually discovered that no. And there are people publishing something related that still didn't understand what's going on. That actually this is the gauge symmetry hidden. But they touch a point here and there without understanding the whole picture. Okay, so with this, I think I have to thank you for your attention.
Thank you, Emanuele. Seems like very interesting observation about gravity. Any questions?
Thanks, Emanuele, for the talk. So on the slide 33, could you go back to the slide 33? I think you mentioned the unitary gauge.
Here?
I think it's the one before, I guess. I think. Could you? The one where you set phi equal to 1? Yeah, that one.
Yeah.
So what I'm trying to understand what the unitary gauge means in this case. So it means that you just can get rid of those fields later on, and then
this gauge fixing is simply in a gauge theory. What you do usually is that you choose the gauge that simplify the field equation to solve them. You can do the same. You can use this symmetry. Obviously, you break the symmetry, but you can choose this gauge. So it just to mention that even in the simplest form that is given by this gauge fixing, you still have a contribution to the physics that you cannot remove. This is basically the message.
I see.
Other questions?
Okay, firstly, congratulations for your seminar.
Thanks.
And I want to ask you if is there some length scale where the conformal modified gravity is dominant, in front of the general relativity?
Well, this is a very old question actually, and the idea is that in general, all the forces at some point should be scale invariant. Okay, and this scale invariance is breaking, creating in some way. So in some way, high energies you should recover this conformal invariance. It's not known which is the scale. You can think about the Planck scale. This is the idea. And actually, it happens that you can generate the Planck scale using this formalism.
Yeah.
So basically, the direct answer is that it's still hypothetical because there are many things to fix to make a strong statement. But the idea is that the Planck scale is the length when you get this kind of symmetry. You restore this symmetry.
You said in one of the first slides that this conformal symmetry is restored in Planck scale, right?
Yeah.
And so it made play a crucial role on quantum gravity.
Yeah, sure. Actually, I didn't mention, but basically, if you have the utilization symmetry, it depends when you try to quantize these theories, and there are similar attempts in the literature. It's very appealing. It's very appealing to think about this symmetry to solve these renormalization problems. But to do it in the right way, you have to study anomalies, because usually you have anomalies associated to this kind of symmetries. So it's not that easy, but basically this is even a possible proposal to quantize gravity.
Thank you.
It's quite natural, actually, because in principle, you should solve the renormalization problem.
Yeah, I think it's a very good question. As far as I understood, so here the symmetry breaking scale is the free parameter, but it's just natural to think of it as a Planck scale. So that something that happens in the theory of gravity, like there would be a gravitational, the Newton's constant, which determines the force of gravity. So it's related with it's a natural scale for gravity theory. So here you have the scale which you think of as probably it's a Planck scale. So some scale where gravity becomes quantum.
Actually, it depends. You can choose that the symmetry breaking is related to something cosmological and not the Planck scale. You can, depending on the choice that you do at the matter sector, you can say that this is broken at other energies. So you can use it even to model cosmological scenario.
Yeah. So if you're smart enough, you can think of some effect that this symmetry breaking can solve in cosmological problem, I guess.
Just a remark here. It's interesting because I work in the last few years. I've been working on modified gravity. This is still a modified gravity, but not that modified because actually it's already there. And one common critic that they move is that when you add other terms to define a modified gravity, you need to introduce a scale, and usually these terms are suppressed and you only can see at very high energies. Well, as you can see here, it's not the same story. Here you can see these effects at any energies. So this is a modified gravity, still a modified gravity, but you really could observe these things at the current scales of energies.
I think. Okay, thank you for the presentation. I have a lot of questions, so I will try be soon. And my first question is: your formalism is compatible to the equivalence principle because you are using non-minimal coupling in your Lagrangian to describe the gravity. So usually this have a problem with equivalence principle. This is very fundamental because it's well tested in lab. So my first question is that. My second question is usually when we are working in general relativity, we have a weak limit. So in the weak limit, we obtain the fluid equations and the well descriptions of the stars using Newtonian astrophysics. So in one point in your presentation, you said that you don't have this kind of weak limit if you don't consider your parameters equal to 0. So usually a weak limit is a dynamical situation, not setting the parameters to 0. So you have some kind of weak limit. And my third and last question is, what kind of measurement you test? I'm trying to say light bending, or I don't know, neutrinos decay, that are well tested of the general relativity. Did you do that? And also, if you do that, the values are compatible with general relativity or are very different from general relativity?
Okay, I start from the third, and I can answer. No, actually, we didn't. We didn't. This is purely theoretical, so we didn't think about a observational test. And to be honest, uh, I'm not that interested. I leave this for the community, the scientific community. I like more the theoretical consistency. It's a matter of taste. But if I have time, maybe one day I will check the observational constraints on this theory. Okay, so this is a proposal for the community. Okay, so I didn't move in that direction so far, but for instance, I'm trying with inflation. So maybe that some constraint will come with inflation. But I really at the moment I'm not doing research in that direction. So I didn't make any test, observational tests. So second, the first question is about the principle of equivalence. Yeah, you're right. Principle of equivalence is broken. But to answer even the second question, here, okay, I said that I recover general relativity when I put, where was it? Where I put xi1, xi2 to 0, right? But actually xi1, xi2 are not fixed. So you can set a scale to be compatible with experiments and with observation. Since it's supposed to work, this theory is supposed to work at the Planck scale, obviously you can go very far from observation as you want. So but you are right. Here the equivalence principle is broken, and this is a point that I plan to work on to find a way to recover. Every time you have this part here that is not 0, you have problems with the equivalent principle. But it's still an open question how to recover it in general without setting a scale that justifies it. And with this, I think I answer even to the second question, right? With this answer, I think that I'm mentioning even the second question, because xi1, xi2 can be, where is this? Where I mentioned here. Okay. So the second question was about the possibility to recovering general relativity.
In the weak limit in general relativity, usually we put the constants and we go to the low velocity and weak field limit, and we recover the complete Newtonian theory for gravity, and we recover for example, conservation equations, like the mass conservation equations or something like that. So the weak limit is very important because you are trying to say that you have a better theory, but in some conditions, dynamical conditions, not setting parameters like 1 or 2, but dynamic conditions,
Sí.
you recover the old theory. But
Yeah.
here you are setting the parameters,
Yeah.
not a dynamical situation.
Yeah, that's what I say. Xi1, Xi2 here are set to 0 to recover exactly in general relativity. But since these are free parameters, I can assume that they are small enough to recover whatever you want. Because I'm free to set them. They are not constrained in this theory. Okay, so I can assume that these are not 0, but are very small. I can assume even that since B mu is massive, I can assume that in some way it doesn't affect because it has a very short range interaction. So I can manage to recover, but not in the common way. Okay. Concerning this theory, if you consider more complicated theories like the interspirable nymph, then the story changes because here it's this parameter that plays the rule to recover all you have in the low energy limit. No, not satisfied. What is not satisfying you?
Well, I think this doesn't work that you would probably most naturally want it to work like it works in relativity in general, right? You can recover. You understand what the limit of small velocity mean, right? That's our
Yeah, here if you assume that these are small, then you are the same setting on general relativity, so the limit that you mentioned is the same.
But I'm trying to say that usually when you have, for example, quantum field theory, you have a propagator that mediate some kind of interaction. So Fermi usually used Fermi first moment use a four-leg theory, and when the standard model was developed, we see that the Fermi theory is only an approximation for the standard model in some kind of energy scale. But uh, anyone put this value of the energy scale is the weak limit that give you that. So saying to the parameter is 0 or next to 0 usually don't resolve that because it's not a dynamical choice. It's not physical situations that are telling you the limit.
I see the point. You mean I had to compare the Xa1, Xa2 with another constant to make the limit. This is the point. Well, actually, I didn't do that. Now that you mentioned, should be interesting to understand the low energy limit. I don't even understand in this kind of theories what does it mean low energy limit, because you don't have coupling constants. They are fixed because you don't have scale. So I'm not sure how to answer to this question because you don't have quantities to compare. You don't set a scale. You don't have a plane scale. You don't have anything. The scale is after you do a symmetry breaking, then you can set a scale through the mass of V mu. Then maybe you can do that. But I didn't. So did you get the
Okay,
point now?
yeah. Well, let's see if there are other questions. No. Okay. Yeah, I think it's an interesting discussion. I mean, I would be probably more optimistic in place of Emanuele, and I would say, yeah, I mean, this is a theoretical study which, as far as I understood, studies a more general theory of gravity from just first principle study of theory of gravity, and then and what is claimed here is that well, there's some problems in the more general formulation, but you can solve them by interpreting this as theory with some symmetry and with some gauge field. And of course, it's very interesting if this is true, then it's very interesting whether this result can be somehow used to interpret some physics, real physics that David was mentioned, for example. Yeah, so yeah, of course, that's very interesting. That wasn't done yet, so maybe it will be done sometime.
Yeah, the point is that this is work in progress. So there are many things to do, like understanding the low energy limit once you set the energy scale. There are many things to do, and
Okay,
the
so if
moment.
there are no other questions, let's thank Emanuele again.
Okay. Thank you.